This section is 2.3, polynomial functions, finding the zeros of a polynomial function. And I know that I get really excited about this section because it's one of those to where we actually get to use a lot of things that we had seen in prior lessons come together and see how cool it is that we actually can be looking at a function and being able to graph it without a calculator. So the first thing we're going to realize is that zeros, solutions, roots, and x-intercepts, all four of those words mean the exact same thing. We're going to be focusing in on the word zero and on x-intercept tonight actually, because I'm videoing at night. And because we need to know what the x-intercepts are in order to graph our function. Before we get started though, I want to review a little bit on end behavior, and I'm just going to put this up here at the top of the paper. End behavior, EB, get it? End behavior. And with end behavior, we have, let's say that we have a function, negative 3x squared minus 6x plus 2. Okay, just a random function that we have. I should put, if I want to be legitimate, function equals negative 3x squared minus 6x plus 2. If I want to find the end behavior of that without graphing, I can look at that algebraically. And the first thing I'm going to look at is the leading coefficient. And I'm going to ask myself, is the leading coefficient positive or negative? In this case, the leading coefficient is negative. And what the leading coefficient does, it tells us the end behavior. Now granted, the big umbrella is end behavior, but the leading coefficient tells us how does this graph end. And when the graph ends, we're looking at it in terms of to the right of the y-axis. Is the graph going to be going up to positive infinity? Or is the graph going to be going down to negative infinity? And if the end behavior, if the leading coefficient is positive, then it ends positive. If the leading coefficient is negative, the graph will end negative. In this case, it is negative. So I'm going to say that the graph will end negative. Then, once I've determined the leading coefficient, then I'm going to be looking at the degree. And then with the degree, I'm going to ask, is it even or is it odd? And that's going to tell me my starting behavior. So where does it start? To the left of the y-axis. If it is even, then the starting behavior will be the exact same as the end behavior. If it is odd, it is going to be opposite of the end behavior. So I see that I have a 2. That means that it's even. Even means the same. It's going to be the same as the end behavior. So in this case, they both will be down. So I have an end behavior of down, down with negative 3x squared minus 6x plus 2. So again, let me recap really fast. Leading coefficient, positive or negative, tells us our end behavior. If it's positive, it's ending up. If it's negative, it's ending down. The degree, if it's even, it will be the exact same as the ending behavior. If it's odd, it's opposite of the ending behavior. Okay? So just a little recap on that. So what we're going to do here is we're going to find our zeros, and then we're going to then use the zero product property to find the x-intercepts, and then we're going to graph it. So the first thing I do when I go to factor this is I'm going to pull out a common factor. And I see here that I have a common factor of x. So I'm going to factor out an x, which leaves me with x squared minus x minus 6. I look at what's inside the parenthesis, use my little diamond method, two numbers that multiply to give me negative 6, but add to be negative 1 is negative 3 and positive 2. I almost wrote a negative there. It should be positive 2. So therefore, because the leading coefficient is 1, I can insert those negative 3 and negative 2 directly into my parentheses as such. Using the zero product property, I set each one of those factors equal to 0 and solve for x. So therefore, I have a 0 0. I have a 0 at 3, and I have a 0 at -2, which means the graph is going to cross or touch the x-axis at 0, 3, and at -2. I'm going to go ahead and factor all 4 of these, and then I'm going to come back and we will graph. The second one, I can pull out a common factor of 2x, which leaves me with x squared minus 2x minus 3. Again, using the diamond method for factoring, I want two numbers that multiply to give me -3, but add to be -2. That's -3 and 1. Again, because that leading coefficient is 1, I can insert the x minus 3 and the x plus 1 directly into those binomials. Set each one of those equal to 0 and solve. And I get an x at 0, an x-intercept at 3, and an x-intercept at -1. Coming down to the third one, again, I have a common factor of x, which leaves me with x squared minus 8x plus 16. What's inside the parenthesis I get to factor. Two numbers that multiply to give me a positive 16, but add to be -8. We see that that is -4 and -4. So my -4's go in to my parentheses, again, because the leading coefficient is 1. I recognize that I can also write that as x minus 4 quantity squared. Set both of those equal to 0 and solve, and I get x is 0 and x is 4 as my x-intercepts. The last one is already factored for me, so I'm going to take each one of those factors, set each one of those factors equal to 0, and solve. So I get x is 0, x is 1, and x is -3. Okay, so now with that, the factoring done, what I have done is I have found all of my zeros. I found my x-intercepts. Now what our goal is today is to actually graph this, make a sketch of this graph without a calculator. So I found my zeros. Next thing I need to do is I need to find out my end behavior. And using the little gimmick that we talked about at the beginning, I look at my leading coefficient, and my leading coefficient is positive. Okay, so my leading coefficient positive means the graph is going to end positive. My degree is odd, which means the graph is going to start opposite of the way it ends. So I know the graph is going to start down, so it'll start in the third quadrant, and it will end in the first quadrant. I know that. Now what I don't know is what happens in between the end behavior and the starting behavior. So let's go ahead and let's put on our coordinate plane our zeros. So I'm going to have a 0 at -2, a 0 at 0, and a 0 at 3. Okay, so I know the graph is either going to cross or touch this x-axis in those 3 spots because of how we solved. We factored, we set them equal to 0, and we found those to be our x-intercepts. I know the graph is going to start negative. I know the graph is going to end positive. So I know that. What's happening here? Well, we're going to jump down, and we're going to talk about a word called multiplicity. This is a new word for most of us. And what a multiplicity is nothing more than the exponent on the factor. Okay, so it's nothing more than an exponent on a factor. Now, we must be in factored form in order for this, so it must be factored before we can find out our multiplicity. And if that exponent on the factor is odd, then the graph will actually cross through that x-axis. If the multiplicity is even, 2, 4, 6, 8, then it does not cross the x-axis, and it bounces back is a word that I like to use, kind of like in Pong, where you have like a, like a little paddle at the bottom of the screen. Here's your screen, and then you've got these balls that are coming, and you move this paddle back and forth. And if you move it just right, the ball hits the paddle and bounces back. That is the same situation that happens with an even multiplicity. Now, if you're not really good, like me, and the paddle doesn't hit the ball just continues down, and you lose a life. That's what happens with an odd multiplicity. It actually crosses through, it goes through. So that's how we're going to determine what goes on in between the starting behavior and the end behavior up here. So I look at what is the multiplicity of this 0 at -2. So the 0 at -2 is at x plus 2. There is no exponent, so I assume that to be a 1. That is odd, so that means it's going to go through that 0. Then I have a multiplicity at 0, or excuse me, I have a 0 at 0 with, again, a multiplicity of 1, which is odd. So that 2 will go through, and I just broke my lead, go through that 0. Then I come to my last x-intercept at 3, and that 2 has a multiplicity of 1, odd, so it too will go through. Now granted, I do not know my max or my min exact values, but that's not the point of this lesson. It could be way up here, it could be way down here. The point is just to get a general idea of what that graph looks like, and we have been able to do that given the zeros, the end behavior, and looking at the multiplicity. Let's look at our next one. We're going to look at our end behavior. It's positive, so it's going to end positive. Leading coefficient is positive. I have a degree that is 3, which is odd, which means it's going to be opposite. So it's going to start negative. I draw my graph. I have a 0 at -1, a 0 at 0, and a 0 at 3. I check my multiplicities at each one of those. The multiplicity, well, let me back up. I know that my end behavior here is negative and positive, similar to the one we just did. At -1, I have an odd multiplicity, so I know that it's going to cross through. At 0, again, it's an odd multiplicity because there's not, so we assume it to be 1. So it's going to curve down and come through the 0. And then the last one is x minus 3, again, a multiplicity of 1, and it's going to come through. So my graphs on both of those are fairly similar. Don't get used to that because it's not always the case. Okay, so I look at this third one here, and I see that my leading coefficient, again, is positive, so it's going to end positive. My degree is odd, so it's going to start opposite. So I have the same end behavior, but is the graph going to actually look the same? I have a 0 at 0 and a 0. Oh, my only other 0 is at 4. I only have 2, whereas before I've had 3, which makes sense because my degree is 3, which means I have a possibility of 3 zeros. Here, my x minus 4 occurs twice, so that's why I only have 1. Again, so it's going to come up this way, and it's going to end going up that way. So now, I look at what's my multiplicity at 0. My multiplicity at 0 is a 1, which is odd, so it's going to cross through 0. My multiplicity of 4 is 2, which is even, which means it's going to bounce back. So I'm going to bring my pencil down. It's going to touch the 0 at 4, but it's going to continue right back up again. It is not going to continue down. It's going to bounce and go back up. That is an even multiplicity. That's what I call bouncing back. Then I look at my last one here. I have a multiplicity of 0 here with 1, multiplicity of 1 at 3, and a multiplicity of -3 of 2. So let's put our zeros down. I've got -3 out here. I have a 0 here and 1 here. So there's my 3 zeros, 1, 2, 3. There they are located. My degree, or excuse me, my leading coefficient is positive. I know it's going to end up. My degree, now I'm not in standard form, I'm in factored form. So if I'm in factored form, I'm going to add all of my degrees up, or excuse me, all my exponents up. 1 plus 3 is 4, plus 2 is 6. So I have a degree of 6 because it's in factored form. The degree of 6 is even, so that means if it ends up, it's going to start up. Remember, even degree means the same. So I'm going to start up and end up. That's different than the other three that we've had. So I start with my -3, at the x-intercept at -3. And at -3, I have an even exponent, which means it's going to bounce back. Then I hit 0. 0 has a degree of 1, which means it has a multiplicity of 1, which is odd. So I'm going to cross through at 0. Then I end with 1, my 0, 1, and 1 has a multiplicity of 3, which is odd, which means it's going to cross through at 1. And so there is my general, not exact, but there is my general graph for those zeros with the multiplicities.